Welcome. I would like to talk to you about specialization and optimization of generic functions in the JVM. How many of you are here for that? Yes, please. Okay, let's talk about it. It's a deep dive. I hope you're ready. I would like you to follow along on the slides if you're comfortable doing so on your device. And so, as you can see in very small print, there is a URL at the bottom of this title. And in very big dots, there is also a QR code that you can take. This is my, for the record, copy of the slides, which you're about to see. There's nothing different between what's up on that screen and what's in that URL. But if you want to linger on something while I'm barreling ahead, which reminds me, this is going to go fast. I don't have enough time to fit this all into the 3 hours that we have. So I am going to go faster than humanly possible. We'll see whether I get to the end. But maybe we'll just all be late for the architects meeting, which comes next in this room afterwards. That would be par for me, which I was late for it last year. But I'll make all of you late too. So there's your chance to grab the stuff, and I'll repost that URL as we move forward. And there's a safe harbor statement so that we can all harbor in safe harborage forever as required by law or practice. That was about 4 seconds. So, okay, how do generics work? Don't raise your hand if you've never used a Java generic, but do you wonder how Java makes generics run fast? Do you know how C++ makes generics run fast? They expand a new version for every instance of your generic. If you want to sort a vector of ints with a certain comparator, you get a bespoke piece of code for that. If you want to sort them backwards, you get a second piece of code with its own copy of the algorithm, unless you take special care to factor it so that the two comparators can be passed to one piece of code, which then adds an indirection. Are you familiar with the trade-offs here? If you write shareable code, then you have indirections. If you write bespoke code, which inlines the comparator, I'm talking only about C++ right now, then you get good code, but you get a ton of code, and you can get like huge amounts of code in your application. So it's a trade-off, speed versus code space. This problem exists for the VM, although we try hard in the Java VM to make that not your problem. And that's one of the powers of Java is everything is configured dynamically. You don't need to get everything figured out up front, run the compiler up front, and that's the code you get forever. The VM's actually good at creating code that's better for you over time. So you won't be surprised to find out, A, we have something like C++ templates, and B, they don't work the same as templates. In fact, we operate dynamically in the JVM on what we call generics and what C++ calls templates. We do a single copy of the code, fully optimized for all use cases, which might be slow, kind of like a C++ template that tries to be polymorphic over both the container type and the comparator, if you can imagine that. How many people have written a C++ template that is that polymorphic over both container, layout, and comparator, say, for a sort? Next to nobody. But we can operate on types that are completely unknown, that were even unknown before the application started. So how do we make it work? And maybe there's a catch. Maybe it doesn't always work. What happens then? So I'm going to try to go faster. Here's a running example that I've chosen for today, QuickSort. QuickSort is easy enough to put on one slide. That's the heart of the QuickSort algorithm right there, twice. Once hand specialized to int arrays, and once generically, so it works for all kinds of arrays. And if someone said, no, doesn't work for primitive arrays, John, you're right, we'll get to that. So here we go. This code should not be too surprising to somebody that's run into sorting as a problem before. One of them is generic, which means it can be reused over and over again. I give that a green star because it's really good. But the other one gets a yellow star because it's super fast. It does only one job, and it does it very well, and the VM optimizes it very well. Let's see, I did some benchmarks. we can find out that to an arbitrary scale, which is JMH running on my laptop, it takes 10 microseconds, about 10 microseconds, 10 and a half, to do the int hand-specialized version on a 1,000 element array of random inputs. And the same array sorts, if it's been boxed, an array of boxed integers, takes almost 3 times as long. How interesting. But we would call that in Java good enough. So the green is okay, even though it's almost 3 times slower than the yellow. But the yellow is where we want to get to. So there's a journey. This is going to fill into a 3x3 map, sort of a colored heat map of excellent to good to mediocre and beyond. But this is what we did so far. QuickSort, hand-specialized over primitive unboxed arrays, and QuickSort generic, reusable over, it happens this time, today, integer boxed arrays. And this is for C++ fans. Here's the comparable C++ template. You can see I've made it to be almost identical, except where the languages demand a difference between the two examples. So again, on the right is the Java code, and now on the left is not the Java code that's hand-specialized to int, it's the C++ code that's hand-specialized to vector of t, so it's generic. So it's reusable. It's fast and reusable. Suddenly I have C++ envy. And the speed of the C++ stuff is, you know what? It's as fast as the hand-specialized Java method. The compilers are quite good on both sides. At least on my laptop, I'm using LLVM and JDK 25. By the way, all of this talk is based on JDK 25. Could have been based on 26. I made no VMs were operated on to make this presentation. That's coming in the future. But then when you use C++ with a non-constant comparator, which means like a virtual call through a function object or a function pointer indirection, we drop down below the green zone to the blue zone, which is I call mediocre. So it takes well more than 3 times as slow once C++ adds in that one extra indirection. Java does a little bit better in those cases. C++, though, has genericity in the fast case. The next thing is even slower. Despite the yellow star, I wrote a reflective version of QuickSort, which uses reflection to work on both boxed and unboxed arrays. So this is reusable. This is the envious Java catching up to C++, wanting to make a template-like thing that is polymorphic across flattened and non-flattened arrays. Does it work? Well, there's the generic guy. He looks almost the same. If you look, you'll see some tiny differences. Where does it say a sub high versus get of a comma high? That's the reflection peeking in there. And Valhalla will make that disappear again, but it won't remove the problem. Valhalla will support eventually flat and boxed mixed generics, but it won't take away the problems that I'm talking about today. The speeds are interesting. You already saw boxes 1 and 2. Now boxes 3 and 4, we find that the reflective QuickSort working on boxed things is only twice as slow as the hand-specialized thing working on flat. And it's actually, for some reason, that's an artifact I can't explain, it's faster than the generic QuickSort. That's an interesting research problem. But then when you run the reflective version on the flattened arrays, it is fully as fast within delta of the hand-specialized one. So now we are on the scent of something that works like C++ templates that can parameterize across flat and non-flat representations and take the comparator also and inline that and get you to the range of around 10 microseconds per sort. That's good. I like that. And there is an upload of the sources for this and the benchmark results, so you can verify it yourself. Okay, so that takes us to a new part in our heat map. Now we are in another happy yellow zone, which is reflective QuickSort running on flat int arrays, and it works almost as fast, and maybe someday will be as fast as the hand-specialized one. And that will, of course, remove the pressure to do hand specialization, right? How many of you have hand-specialized an algorithm that should have been generic? Yes, it happens. We want to have that happen less in the future. The reflective case is important because boxing is a lot of extra stuff to maintain. 4 bytes of int payload, up to 24 bytes of other stuff wrapped around it. That's a lot of stuff to take to keep the books on. So the higher footprint, also footprint means bandwidth. If you got more stuff in memory and you're obligated to walk over it, you need lots of memory bandwidth. That's the reason between the yellow and the green in the Java cases of hand-specialized flat ints versus generic non-flat ints. And with Valhalla, we will have many more kinds of flat arrays, which is wonderful. And yet, there's a lot more what I call layout or format polymorphism. There's a lot more different cases for the optimizer to take note of. And the only reasonable way to optimize some of these things is just make a new copy of the whole algorithm for sufficiently different cases, not try to have common code. Did you know that today, Hotspot has sort of as a working rule, there's only one copy of the optimized code for a method at any one time. So we don't have versioning, we don't have specialization. This is a future, and today's talk motivates that future. Valhalla's trade-offs are good because flat arrays, not being boxed, do go faster. So that's good, let's do it. Now, this is a model of Valhalla. I'm not saying reflective QuickSort is any kind of part of Valhalla, but it is a way to predict on top of a stock JDK 25, Java 25, what Valhalla dynamics might look like when optimizing generics that work on secretly flattened arrays. Because Valhalla arrays look boxed, but they're secretly flattened, which makes them fast, which we like, but then it's hard to optimize. So how did we get that code to go so fast, by the way? We got into the green zone, and in some cases into the yellow zone. There's 3 things the VM does, which are its master tricks: profile, devirtualize, inline. And this is a virtuous cycle. These tactics go together in the JIT. Profiling starts in the interpreter, but the JIT uses profile information to then decide where the opportunities are to devirtualize, either by dead reckoning or speculatively. And then once devirtualization happens, then you have a method that you might be able to inline. And C2 is very, very eager to inline. Once you inline, then you can fold everything together into one big IR pot and stir the pot until the soup boils down to a nicely optimized. What happens when you burn soup? That's not the right metaphor. In any case, the stuff that happens while you're stirring the pot is that types and constants and behaviors and formats get pushed around by the optimizer's inference until the optimizer knows the exact shape of everything in the algorithm. There's no mysteries left, and then it can register, allocate, and code select. This, by the way, happens for both the array type and the comparator. Both of them you need to optimize. You need to do the devirtualization trick. You need the exact type of the array, especially if it's a flat one, and the exact type of the comparator if you want full performance. There's a whole long list of things that happen after the big pot is made and you're stirring. Sometimes great loop transforms come out, sometimes other things come out, but I'm not going to go into that. So another way of saying this is, even though Java is very dynamic, after profiling, if you speculate that the profiled behaviors will continue into the future, it's okay if they don't, but you'll speculate that they do, then you can emit code that is monomorphic where it counts. By monomorphic, I mean there's just one set of forms, assumptions, types, knowledge about layouts, which means you get regular native machine code, just like C++ does. Monomorphic code looks like it was compiled by a static compiler, even if it was compiled hours into a dynamic run of your machine. After classes were loaded, after profiles were formed, it still looks static. It might have been born dynamic, all this workload, but the code looks static. Here are the full set of algorithms that I'm working on. It's really just one algorithm, QuickSort, with the Lomuto selection of pivot, which is the simplest form. There's the int QuickSort I showed you, there's the generic QuickSort I showed you, there's reflective QuickSort I showed you, and then there will be a brief peek at the iterative QuickSort. And there's also the C template QuickSort. Here's the code. After you boil down the soup, to whatever it remains afterwards. In our case, it's machine code. This is what the machine code looks like. The green stuff is the checking of your speculative preconceptions. You want to say, is this still the kind of workload I've been optimized for? And it's very fast to check. You check a type, and you ask whether the type of the array, in this case, I think it's the array. No, it's the comparator, right? It's the comparator. Is the comparator the one that I'm expecting? Because I open-coded it later on. It better be the one I expect. If it's not, then I go to the purple thing, which means I'm falling off a cliff. Purple means off the cliff. It means I have to go to something called an uncommon trap, which is very painful, but still correct. And eventually, I might re-optimize and get on my feet again. But the good case is, yes, my speculation is correct. I'm still working on the same kind of stuff I was a second ago. Now I'm going to go into a hot loop. And the yellow stuff, which is the highest performance part, presupposes that I'm using the comparator that I thought I was. And all it does is it loads an int and then compares it against another thing that's in an integer, which is in a register, which is your pivot, and branches greater than or not. That's what you want, right? That's what C++ would do. I'm not saying C++ is the paragon, but if C++ goes fast, then why shouldn't Java, right? This is another explanation of type profiling, which I'm basically going to skip and let you read later on. But basically, if we see a type, we think it's going to continue in the future. And we can tolerate up to 2 types, which leads me to bimorphic profiles. A profile can have 2 types in it, not just one. I might be sorting one moment integer arrays and another moment short arrays. And that's OK. My generic code can absorb that. I end up compiling paths for both of those cases that are open-coded. But it is slower. It takes us into the blue zone. My JMH benchmarks suggest that it's 47 as opposed to 12. So it's 4 times slower. That's not a good comparison. But it gets slower the more types you try to force through the optimized code. So something's going wrong. And in the case of working with flat int arrays, my particular code, there's some artifact which fails. I didn't investigate it. But this is typical. You can't stay on the edge of the cliff very long before you fall all the way off. And so that's what happened here. One input, the VM was able to manage not too terrible, mediocre style. And the other input, it just fell off the cliff. And the algorithms, as you saw, are very similar, but there's slightly different optimizations going on. Basically, you want monomorphic code, which works on just one type. And you can tolerate 2 types. You can write quasi-monomorphic code that's working on one type or the other. But there's a lot of branchiness in that code. And that's going to slow you down a lot. So here's the map so far. We're falling down from the green and the yellow by adding bimorphism, 2 types instead of 1. And the optimizer is still writing one method, one optimized bundle of code that handles 2 types. That's not a trick C++ attempts, nor should it. But the VM does it under the current ground rule that there's just one optimized method per Java method. So here's what the disassembly looks like when things go really wrong. On the left, it's the same as I showed you a second ago. On the right is what happens when the 3rd type comes. I'm really sorry to tell you that 3 is the magic number here. What happens is once the VM sees 3 types in a profile, it says, you know what, this profile, it's dirty, it's polluted, it's saturated, it's so full of information that it can't give me a clear signal. You'd think, well, more information will let it optimize better, but no. Superimposed signals are bad signals, and that's what's happening here. So there is a compare and branch greater than at the bottom of this code on the right-hand side, which is really nice. But you had to go through an indirect call through a virtual table in order to get there. So that compare of W0 is comparing the return value of an out-of-line call. And all the red stuff there is setting up arguments, or more of it is swapping volatile registers in preparation for the catastrophic event of an out-of-line call. C2 does not like to do out-of-line calls, nor does any compiler. So there's some megamorphism going on here. That's the catch. That's when there's 3 or more types. And you know what? For real workloads, there might be 40 types. You might be running Arrays.sort on 40 different kinds of arrays with 20 different comparators. And you should. That's what the VM is for. And it only goes down so far when you get to the virtual calls. Then you're doing multi-way branches, and there's no more cliff. You've fallen as far as you can fall. So monomorphic is great. That's when there's just one type. And then megamorphic is the opposite. It's the other end of the spectrum. It's when everything's a virtual call. And that's just got to be slow. Without type data, those megamorphic calls, they go somewhere you don't know. And the VM has to compile a very conservative call that I showed you the assembly of. There's spilling. This is the performance cliff. And more subtly, without inlining, you can't stir all that IR into one big soup pot. You have a little soup pot over here where the comparator code is. And that's really good code, by the way. It's just a few instructions plus procedure linkage. And then over here, I just really want to get one spoonful of that soup, please. But I've got a static IR bundle here, and it has to emit spills and argument and linkage and procedure linkage and return. And finally, you can get that little couple instructions over here. And that happens dynamically. Array access slows down too. Let's see here. There's extra work for the reflective case where I artificially said, let's do flat and box mixed together. But Valhalla is going to demand this a lot. So here's another way of looking at it. If I am running sorting on integers, and it's just integers only for a while, then my performance color is yellow. I'm doing great as C++ doing its monomorphic thing. If I add some longs as well as some integers, some long arrays of longs as well as longs of integers, and long compare as well as integer compare, well, then there's 2 things, and I'm going to go to mediocre performance. And then the red case is when you get the third thing, the shorts arrive, and then you're done. Here, showing at not the assembly level, but at the code level in the generic QuickSort are the hotspots. When you load A sub high to get the pivot, you are doing something polymorphic because you don't necessarily know whether it's an array of longs or an array of shorts. And in Valhalla, those might have different layouts. Today they don't, but they might in Valhalla. This is not the reflective version, so that's not a huge problem here. The comparator is a problem. You don't know if it's long.compare or integer.compare. You're out of luck. You're going to call the comparator API through the vtable, and that's really slow. And then swap also goes back to the array and moves things around. Again, if the store check that you have to do is different for a swap when you're swapping 2 integers in an integer array versus swapping 2 longs in a long array. And I'm talking with boxes. Boxes or not, the data motion is slightly different. So there's some virtualization even for reference arrays. Here's the scorecard. Falling down from bimorphic to saturated profiles, you can see that the performance gets much worse. From 12 at the very best down to 70 at the very worst, across the varying algorithms. So that's a performance cliff. It doesn't get worse than that, but it gets pretty bad. And here's our heat map. This is setting up the problem so far. I'll give you the solution in a second. When I say the solution, that sounds very hopeful, doesn't it? I shouldn't have said that. But you can see there's a mixture of blue and purple, which is mediocre and catastrophic performance for different cases. And again, there's a lot of chaos near the edge of the cliff and at the bottom of the cliff. You don't know exactly when you're going to fall off, right? It's hard to tell what the JIT's going to do and what kind of mood it's in, and whether the profile is clean enough to move forward or not. It would be really nice to get that stuff right, huh? Let's iron this out somehow. It's time for poetry. I think that I shall never see type inference which pleases me, nor inference of nullity. Such inference must be poetry. Generic software troubles me. Despite the seeming clarity, dynamic calls clash secretly. The VM runs them sloppily. Then Valhalla's subtle flattery. See what I did there? Arrays get laid out pointer free with nicer heap locality, but watch that dynamicity. Off the cliff you go. So I'm going to still try to go fast. So we need something that will compensate for the extra dynamicity and allow us to still have our little windows of static sanity so that the performance has the desired quality. I'm still rhyming in my rhetoricity. But the thing we need to do somehow is be able to claw back those static optimizations and claw back that enjoyment of monomorphic code. So if we can set our boundaries properly, then I think we can get there again. We can get something that has all the good parts of C++ templates with none of the bad parts. What are the bad parts? Well, you have to decide it all up front in advance. And your template, even if you run it just once, has to be fully instantiated. You know, you could list these out. With Java Hotspot, you only need to work hard on optimizing the parts that matter. It's okay if the program runs slow, as long as it doesn't run very often. But the parts that run often must not run slow. So that's why Hotspot concentrates on just-in-time compiling. And so the hot parts need to have all those tricks, the devirtualization, the inlining. They need to benefit from some form of profiling. You need to get rid of all that spilling and virtual dispatch. So what if we could profile each call site? That would get you closer to something like C++. It might be too far pendulum swing in the other direction, but maybe that would help. Maybe several call sites might conspire and say, we're all in the int club, and we're all using the integer compare comparator, so we're all going to call this algorithm, which is cloned and optimized just for us. And these guys over there that are doing longs, they get a different one that's cloned and optimized for them. But maybe they don't do it that often, so they don't even get the optimized code. They just use the common code, which we have today, which is generic and not bad, but not great either. So getting a clean profile might help. Maybe we can then statically optimize each distinct class of call site for the use case that is optimal, for its own optimal use case. Treat it like a template. And Project Valhalla, acknowledging this problem, has on its future roadmap something called specialized generics, where a call to a generic method, like we're using today, might actually redirect and go to a fresh copy that is specialized for that one particular version of the algorithm. We don't have this today, but is there a way we could approximate that? I wonder. One wonders. If you had something like specialization for methods or for classes, array list specialized to be a flat array list of something, array list of lizard, or array list of point. But I'm talking today about algorithms, which I think are more fundamental and easier to reason about. What if we could get something like the hand specialized int QuickSort through some sort of generic specialization mechanism? I would like to call the thing that you get out of that specialization process a method which is a species method. So class is a unit of taxonomy. Here is a class, here are the methods of the class. But once you specialize all or part of the class, you get a smaller piece of the taxonomy, you get a species. And the VM should do this transparently. I shouldn't even have to tell you about this, right? Let's all go home. Just wait for us to get it right. It's hard though. So I'm sharing it with you in the interest of transparency. Do we need new language features to unlock this kind of thing? Maybe. That's an open question to me. The other question is, how far can we go transparently? That's a very interesting question to a VM geek like me. So maybe steered by the right kind of subtle hints and tea leaf stirrings in the class file, maybe we can tell when to go to that kind of specialization, get that species, get the int species, get the long species. Oh, you're doing the reverse comparator. That's a different algorithm. Or maybe the VM says, that's not often enough. You're going to go generic on that one. So let's continue to try to get full optimization of the most dynamic code and dynamic workflows possible, because that's kind of the superpower of the Hotspot VM. By the way, there is a connection to Leiden. All of this stuff that we're doing can, in principle, be modeled in a Leiden training run. The training run can say, you expanded this template. You declined to expand these templates because they weren't called long enough. Let's assemble you the templates we think you'll need for the next journey. So it packs a little lunchbox, also known as a AOT cache, and puts those methods in there and says, here, you'll enjoy this when the time comes. So there is a Leiden story that connects to all this. It's not relentlessly dynamic. We've experimented with this stuff. There are several ways you can attempt to attack the problem. I'm going to share with you 2 experiments that kind of worked. Today's first experiment is to use hidden class. How many of you know about VM anonymous classes and hidden classes? Dude, that's pretty good. It's a very obscure feature. But basically, it allows you to load a piece of class with a class file without committing to it being in anybody's namespace. So you can load as many of them as you like, and they can be actually docked into other namespaces, so they can actually access the private methods of the class that they're docked into. So what if we clone the class file for QuickSort into a hidden class? And then instead of call the original methods, call the cloned methods. The way you do that is like you make a method handle on the hidden class method, and then you invoke the method handle. You could also do it with interfaces. I didn't bother to do that because I like method handles. So maybe we could in future versions, we could like heuristically wait until the hotspot develops for a particular species of call, and then instantiate the hidden class, and then let that thing develop and warm up, and then the optimizer would see just one profile, a pure uncluttered profile, and generate monomorphic code just for the callers that were redirected to that particular species of call site. It might work. There's another one coming too. So what we do is, that's essentially the code. It's not much simplified for the slide. We read templates using the get resource, which is a very old API in Java, to reflect on the class file bytes of the algorithm. And then you reload the darn thing as define hidden class. And now you have a fresh copy of QuickSort, either reflective QuickSort or generic QuickSort, you choose. And then you get the method handle, and that's your entry point. So there's a whole lot of manual stuff to do. If you're expecting to see automagical stuff, this is not your talk. This is a performance investigation about what are the resources of today's VM for solving this very hard problem. And I think this is, in brackets, a kind of a generational level problem for Java. Fast startup is one of Java's big problems. But also specialization of generic code. Cliff Click has called it the inlining problem for a long time. How many of you read his blog entries on the inlining problem? Oh, come on, it's good. It's not the inlining problem, folks, though. It's the specialization problem. I call it the loop customization problem. And it's not the inlining problem because if you have a stream that's parallel and it's running its tasks, subtasks on multiple threads, you are far beyond what inlining can help you with. You need specialized versions of the code which can be forked out onto a worker pool. Anyway, the transform works. Look at those times. We have a saturated profile for the generic QuickSort at 70 microseconds. We apply this trick to it. It's one weird trick. You see that on the internet all the time. And it gets back to its original performance as if the profile had never been polluted. And let's just all agree to say it's obvious in hindsight, but I'm kind of pleased at having figured that out and how to take the wormholes necessary to get to this outcome. If you do it to reflective QuickSort, the results are even more astonishing. You get back to the handwritten speed, which is the same as the monomorphic reflective QuickSort speed. So number 4, the yellow box 4 up the top, was we saw a moment ago when reflective QuickSort had a monomorphic profile and could generate monomorphic code. And then it fell off the cliff even on the second type and got to 60 from 12. it climbs back up off the cliff, dusts itself off, and says, I'm back. I'm as fast as hand specialized code because I had a clean profile and you kept your longs and your shorts away from me. It's not a panacea. Everything gets cloned, which is a little bit wasteful, but it's also kind of good because as long as your algorithm fits nicely in one class file, all the helper methods are cloned too, so they all get their cloned clean profiles. It's just an artifact of how define hidden class works. So I could say I got lucky for this talk. I did design define hidden class. So maybe it was planning. So there is a problem though if you have two files or even a nested class. That's another feature I had something to do with. If you have a nested class, then you have two class files and this trick doesn't work. So it's not a complete solution. But it is nice that even a recursive algorithm will work. It's not always true that an arbitrary optimization or a transform of a recursive algorithm will apply fully because things get weird when you get into deep recursions. But this one works. I have no story to tell you right now about what to do with secondary class files. That's future work. That would be future work for Valhalla, because Valhalla is going to need to grapple with this somehow. And code cloning can be wasteful. What if there are methods in your class file that don't benefit from the monomorphization? You really want to have the VM concentrate on where there's opportunities where cloning would help rather than just clone blindly. There is on the books a very large VM enhancement, probably the largest ever, for Valhalla, for specialized generics, and you'll see that in the slides later on, but it's called the parametric VM. I'm not going to explain it to you. It is a multi-week briefing. So there's another way to get the effective monomorphic fully static optimization, and that is to inline. So solve the inlining problem by inlining. That took a long time to figure that one out. What was hard here was to actually get enough control of Hotspot's inlining heuristics to make this experiment work. It was very difficult because I was using Hotspot as a black box. Well, I know how it works inside, but I was not changing anything about the VM. And so the cheats were minimized. But what's interesting about a full inline is you get type information not from the profile, which is a property of the code that's being called, but you get type information from the caller, which is a property of the caller code. And so the caller might be able to tell you, hey, I'm passing you an int array always. I'm statically typed to do that. I don't care how generic you are. I just care about the ints. The caller can tell you that. The caller can say, I'm always passing you integer compare. I'm not passing you any other comparator. Will you please just do what I want? Just me. Focus on me. And so inlining lets you focus on just that one caller, and that's pretty good. So I cranked up the inlining, and there was a way to force it. And this doesn't show the way I forced the inlining, but it involved another hidden class to trigger method handle customization. But that's all detail. It's the force customize operator, and no, I'm not shipping that, me personally, at any point. Maybe someone else will make that decision for me. But the basic idea is take the generic method handle and then force it to take a constant comparator and then force it to take a particular kind of array and then compile that. And C2 sees that and says, oh, I know what to do with that. I know what you mean. And it generates the hand specialized code. What's really interesting here is if you turn off type profiling, this runs just as fast as ever. That's really cool because you can just basically nuke the type profiler. And this inlining tactic works, which is a suggestion that maybe we should do both and, right? One doesn't subsume the other. This one is very vulnerable, however, to other inlining artifacts, including inline small code. How many of you have ever run into inline small code? Well, yeah. Yeah. It's just a bad thing. I remember when we had to invent it. It was for a bad problem. We still don't have a better solution for it. Somebody tell us how to fix inline small code. Basically, it says the VM is telling you, I worked so hard to compile this method, I am not going to inline it for you. You use what I compiled for you before. That's the VM saying that. And that way, if you try and do this inlining trick, and you have a compiled version of QuickSort, and it's really bad, I mean, it's mediocre. Sorry, not bad, mediocre. Or maybe it's even off the cliff. And then you try and inline a really hopeful call site that says, no, I'm just doing string sorts, and it's just string comparator. Please, please, please inline. What did I tell you? I worked so hard to make this losing method that's off the cliff. You're going to eat what I feed you. That's what inline small code says. So I set the parameter to 1 billion to override that particular effect. Other bad things happen if you do that in practice, so I'm not saying that's the go fast switch. So here's the whole map. We started in the upper left corner with hand specialized goodness, which is totally competitive with C++. We recovered it with monomorphic profiles on the upper right-hand corner with the reflective QuickSort on flat arrays. The green one, the regular QuickSort, he's a little slower, but that's just because of boxing. It's nothing. It's not our fault today. But getting rid of boxing, that's a really good thing to do. So you go to flat arrays and then things get twice as fast. That's cool. But then you start to add more types, and as you go down the heat map, on the right-hand side, you go through bimorphic troubles down to the bottom of the cliff with saturated profiles, and it's very, very sad. And then you have two possible repairs which work on the current stock VMs with the right tweaking and cajoling. So that's basically it. That's where we got to. With C++, there's not so big of a cliff, because there aren't that many different things that can happen. Everything is known up front at compile time, and your giant piece of code is what you get, and it performs the way it's going to perform forever. There's no dynamic optimization or any of that newfangled nonsense. But I will say that the QSort function, which is C, not C++, has the same kind of artifacts. I tried several different sorts, and they all kind of have the same quirks. You know, if you can inline it and you can specialize the data container and the comparator, good. If not, then you're going to get to the same cliff kind of location. I mean, cliff, geological cliff. So C++ can't recover at all, not dynamically, because it has incomplete dynamism. There's no way to fall back to the big generic method that might be at the bottom of the cliff, but at least it runs correctly. There's no sampling or dynamic profiling to inform dynamic optimization. It's just static compilation. The JVM has the additional features that lets it recover better. I talked a lot about the yin-yang of dynamic and static in another paper last year, which I'll leave you the link there. It's also in the references page at the end. So I'm going to include C++ on the journey also, just for completeness. On the far right is a column of a custom template, which has performance very similar, although not quite as good for some reason, as the VM template-y things. And then C++ has its own fall down. As soon as you need to deal with two types or two comparators, then you start to go through vtables and function pointers, and that takes you into the blue zone. And there is no cliff for C++. That's because C++ can't even spell cliff. You can't get there. You can't be dynamic enough to even encounter the cliff with C++. So it's not a thing. You decide whether that's good for you, but I think I would like there to be a master instance I can fall back on. I would like a profiling framework that's always on. I would like not to have only static compilation, but also dynamic recompilation. Some of you probably agree with me. I'm dumping on C++, but we love it too. There's a lot more questions in the 3 hours remaining to discuss. Could we auto-specialize TimSort, which is the JDK algorithm, so that it's immune to profile pollution? I tried it yesterday. It works. That's pretty cool. I'm not going to, no PR yet. The policy for when to specialize is the non-trivial part. Remember what Brian said yesterday about good ideas? Specializing TIM-sort is a good idea, which means it's 1% of the work. But, you know, that's something to look into. So all of these questions, maybe the VM should take more of the burden of specializing and managing specializations and auto-specializing. Maybe the language should be extended. Maybe we should have more generic functions and fewer hand-specialized functions. How can we steer toward that future? And how can we get how can we make a future where people routinely and confidently code generic functions that will specialize with the same confidence that they would code a C++ template and just know it's going to specialize? That's the future I want to get to. This is a step in that direction. These are some ideas in that direction. There's a lot of people thinking about this stuff, so this is just my modest contribution to it. Since we're talking about AI this week, I'll just say Opus 4.6 was really helpful. It wrote the first drafts of some of these things. I said, give me QuickSort. It said, here's your QuickSort. That's cool. I had to rewrite it. That's fine. It's faster to debug a bad code than to debug a blank sheet of paper. I asked Claude for a poem. Oh, Claude's really good at reviewing. Claude reviewed these slides 3 times and found sequence orders, omissions, bug in my slide code, reviewing the PDF. Pretty cool. I asked it for a poem about its role. It said, compiled from electricity, I match your patterns context-free and inline what you teach to me, then specialize it helpfully. I say, Claude thinks, therefore he seems to be a topsome statisticity, a well-trained, feigned complicity that reasons through my mystery. I will also say that the inventor of QuickSort, in the last 5 seconds, the inventor of QuickSort, Tony Hoare, passed this month. Rest in peace, sir. I have been inspired by his Turing lecture back in 1980. Here's some juicy quotes for you to read later. But there's something between there's a connection, a deep connection, which he was a champion of, between clear thinking and computer languages, which has always excited me since I was a teenager. Further reading, links, check it out later. Something for the lawyers. And thank you.